today I will share something about the interval analysis on time scale and its application with the interval differential equation. And this zone work with my supervisor, Professor Baruch Schneider, and our colleague, Lynn. Oh, sorry. Oh. Okay. And here is my outline. I will talk something about the time scale calculus and for interval value function on time scale. And the section 2 and 3 is my main part will be about the diamond derivative for interval value function and application. And in this talk, we will answer two questions. The first one, why we need these concepts. And the second one is how efficiency is a. So we know that the differential equation is the power, the most powerful and meaningful to describe and study natural phenomena, and it helps us to describe the natural phenomena by the mathematical models. But in some practical cases, and because of the imprecise measurements or the indeterminacy of the event, is a make the uncertain or the vagueness. So how can the question is that how can we overcome these drawbacks? So in this case, we will use the interval differential equation or the fuzzy differential equation to try to describe this. So in this talk, we will focus on the interval differential equation, but in generalized domain is called time scale. And here is some basics about the intervals. We will denote I in the set of on non-empty closed interval of R. And here is the Minkowski addition and the scalar multiplication between two intervals. And when we consider the interval differential equation, we need the derivative. And the problem is that we try to define the difference in generalized case, because the difference very important to define the derivative. So you see the generalized Hukuhara difference is a very well-known difference. And for two intervals, we define the generalized Hukuhara difference in like this form. And if we denote the length of the length of the interval A by this form, and we will have the first case like this, and the second case like this one. So let me talk something about some differences. For the we have the Minkowski difference like this, and actually it's always easy, but we don't have the very important property that for A plus with minus A is not zero. So in 1967, Hukuhara he proposed the new difference, and it's not always easy. The problem is for if the length of the interval is less than the the length of interval B, and it's not easy. So in 2009, and Stefanini and his colleagues proposed the new one is called the generalized Hukuhara difference, and the important thing that is always is it for any intervals. For example, we consider the two interval 2, 3 and 2, 5, and in this case, the Hukuhara difference is doesn't exist, but for the generalized it is it and equal to 0. So for our purpose, we need the Hausdorff distance, and it's the maximum. It's 2 norms like this one, and here is some basic property of this distance. So let's talk about the time scale. Time scale is a non-empty closed subset of R, and it's the first introduced by Stefan Huger in his BSD framework in 1988. And for on-time scale, very important operators is the forward and backward sum operator, and it can be defined in these formulas. So here is the example for the forward and backward sum operator on time scale. For example, we consider x, z for x greater than 0, and we consider it's like a discrete. We consider t, the point t here. So in this case, the forward operator sigma t will be here, and the backward will be here. And the another one for time scale t, and this one for we consider t here, and we can see that this time scale is the left length. So for the rho t equal to t, and the sigma t will be here, and also for the another time scale for q belong to 0, 1, and in this case we will call it the quantum time scale, and and for our purpose we need the kappa set with the definition applies here, and for the t kappa will be the t kappa minus m, for m is the left scatter maximum of t, and for the t lower kappa can be defined the same way, and we denote the t kappa in the intersection of t these tests, and also we denote the mu ts equal to the forward operator of t minus s, and the same for the nu t. And so here is the definition of diagonal differentiable for the real value function from the time scale t to the real number, and if the function f is called diagonal differentiable at the t if there is a real number denoted by this, and satisfy for any epsilon greater than 0, and there is the delta greater than 0, such that the formula is satisfied. And so for our need to define the Diamond derivative on time scale for the interval value function, and we need the limit. So we define the t limit by the sequence of the interval function based on the Hausdorff distance, like this one. So here is our main definition for the interval value function. We consider the interval value function f, and for tau belong to 0, the interval 0, 1. And in this case, the generalized Hukuhara diagonal derivative for the function f at the t can be defined in this formula. And here is the how does distance between this term and this term. Yes, it's like complicated, but we can describe in the easy way. And in this case of S is belong to it for the X in not sigma t, and for S also not the pro t, and we can present by in this formula. And it's from the definition of the t limits, and we can describe this one is the t limits of the term. And for the special case, for the time scale t is the for the t is an isolated point, and the diagonal derivative can be defined without limit, like in this form. So let's also consider the example for the time scale t is the x z, and from the theorem we can see that the diagonal derivative can compute in this formula, and we choose for tau equal to 1/2, and we get this form. And this one is like the edge symmetric difference for the interval value function. So this theorem says that some property of the differentiability of the function f when f is differentiable at t, and then f will be continuous if one of the following statements is holds. The first one for t is the isolated point. The second one is for the dense point, and the third one for the t is the right dense and left scatter point. And we need to add some more condition for the existence of this limit. And for the fourth one is similarly. And the next theorem says that if the interval function can be represented by the formula that for like the level, the lower level and upper level, like u and v. For u, v is the real value functions, and the length function of f is the monotone on the neighborhood of t, and then if u and v is diagonal differentiable at t, and we have the first one, the derivative of the function f can be represented by the derivative of u and v. And in the case of the length of the function f is decreasing, and the derivative of the function f can be represented by the inverse with this one. For this one, the derivative of v and derivative of u. And from this theorem, it leads to two kinds of differentiability. This one, if the function f can, the derivative of the function f is like this one, and we will call f is the first differentiable at t, and for the second one is the second type differentiable at t. So into more detail, we can consider we can consider the simple example. For the function, we consider the function f from the interval 0 for on time scale t, and they define like this one. And here is the graph of this function, and we consider h is 2.1. And here is the derivative, the diameter derivative of this function, and you can see that in this the function will be the first type of differentiable, because it's the lower branch, and this was the upper range. And when this one is changed, and we will call this one on this interval, and the function f will be the second type of the differentiable, and for the third one will be the first type of differentiable. And for application, we consider the special time scale like this one, and we consider the function ft like this formula, and this function like is a tension of the function, the real value function ft, lowercase ft. So here is the graph of this function. Is for the blue ones is the lower branch, and the red one is the upper range, and this one is the real value function ft, and we can see that the function ft is the extension of this one. Yes, and this one is the interval value function. And here is the derivative, the diamond tau derivative of the function f with the different level of tau, you can see here. And we want to compare why compared to answer the question that why we need this derivative. And in this case, we compare with the delta and the nabla ones. And we take this one average of the lower and upper range. And we can see in the figure that the diamond derivative is very near with the classical one for the derivative of the function f, but for the delta and the nabla one is quite different. And in more detail, we can see in this table for the we use the Bruce mean square errors to compare it, and you can see that at for the case tau equal to 1/2, and the error is very small in comparison with other. So in this case, we can see that with for the tau diamond, with the tau is 205, is a more balanced and so more accuracy. With this one is like the symmetric in the classical analysis. We have the symmetric difference, and so in our case for the interval value function for tau equal to 0.5 is more balanced. And here is the Bruce the relative errors, and so we can see on this graph, and for our case for the diamond tau is very small errors. So the another examples we will apply for this derivative for the interval differential equation, and we consider this system and with the initial condition like this one. And for the operator dt, the derivative of the interval value function is that the diagonal and the delta and the Nabla derivative. And this problem is extension of the ODE can be right in this form. And this problem can be described in the level set in two systems like this one, and use the derivative, the definition of derivative diagonal, and we can get two systems like this one. And for details, and we consider the interval differential equation like this one, and this one is an extension of the problems, and we use this differential equation to compare with this one. So here is the solution of this problem, the problem 10, at the tau equal to 1/2, and here is the second. In the comparison with the delta and the Nabla one, you can see that the solution of the system with the diagonal derivative is a very nice solution in comparison with the Nabla and the delta one. And we use the root mean square errors, and see that for the model, so with the diagonal derivative with the tau equal to 0.1, the error is very remarkable in comparison with the delta and the Nabla one. So that's all for me. So in this talk, I mentioned about the diagonal derivative for the interval value function, and via the generalized Hukuhara difference, and we consider its application to the formulating the interval differential equation on time scale. And we realize that the diagonal derivative is the best tool to this issue in comparison with the well-known derivative, namely the delta and the Nabla ones. And for the future works, we plan to apply for the classes of interval differential equation or fuzzy differential equation with the diagonal derivative. And we also consider about the existing solution, also the solution methods. And next, we can study the higher orders of the diagonal derivative and its application to the higher order interval differential equation or fuzzy differential equation. And in the currently, we are considering the special time scale. It's a TQ like this one, and this one called quantum calculus, and we will use this one to study the fuzzy Q symmetry variational problems. And that's all for me. And here is some references. And we have the result on the published in last year on the delta one. And that's all from me. Thank you for your attention. Thank you so much.